So I'm going to start off with a slide that a lot of you are probably familiar with from your childhood. If I can get this slide to switch here. There we go. So this is the old Where's Waldo game that a lot of kids play. So the idea there is to find that character down there in the lower left corner within that sea of characters that's depicted in the larger picture. So my version of Where's Waldo is, where's the database? So this is just one of many similar infographics that I scraped off the internet that kind of show you the, well, as the title says there, the Internet of Things landscape. So we've got, industrial internet stuff, connected home stuff, connected car stuff, a lot of infrastructure for building the Internet of Things. But what's glaringly missing is any mention of database systems on edge node devices. As Ted said, the things that make up the Internet of Things. Which is, like I say, it's a glaring admission and really rather mysterious. And as Chris alluded to, this is something that we've been doing for the better part of 16 years. We used to just call it embedded systems. Today, Internet of Things is the marketing term, which is good for us because it's bringing a lot of visibility to a space that we've been in for quite a few years. So we appreciate all the visibility that it's bringing. We just wish there was more discussion of the database management aspect of it on embedded devices. To the extent that databases are being talked about within the Internet of Things, it's in the context of the big data that's generated by all of these things that make up the Internet of Things. So I'm going to compare and contrast a little bit of the different characteristics of database management systems that are suitable for doing the big data side of things versus doing the embedded systems or the things side of the Internet of Things. So for the big data side, of course, you're going to have big honking servers. The one that I've pictured here happens to be an IBM Power 8 system that we've done a lot of work with in the capital markets. But they're going to be big servers with a lot of cores, tons of memory, huge storage arrays for managing all that big data. They might have unpredictable content. So one of the hallmarks of the Internet of Things is that there is going to be billions and billions of devices that are connected to this Internet of Things, and that new devices could be emerging at any time that we hadn't seen before. And so these big data analytic systems need to be able to deal with new types of data that are being generated by these new types of things in the Internet of Things. And when you talk about those types of requirements, people tend to think in the context of NoSQL systems because they don't have rigid schemas, and therefore they're more adaptable to dealing with new types of data that are being generated by new types of things within the Internet of Things. Doesn't necessarily have to be that way. If you're working in a private cloud and the universe of things that are going to be connected and generating big data for you are well known, then you don't really need that flexibility, and you can stick with a more standard architecture. And when I say standard, I really mean SQL, so that you can draw from a much larger pool of talent out there. The challenge, or a challenge, with NoSQL systems is there really hasn't been any standards that have emerged for those. So the way that you interact with a MongoDB system is very different from the way that you interact with a CouchDB system or a Redis system or a MarkLogic system and so on and so forth. Whereas SQL, by and large, is SQL. And it really doesn't matter if you're dealing with SQL from McObject or Oracle or the Microsoft Azure Cloud. SQL is pretty much SQL. Yeah, there's different subtle differences between the dialects of SQL, but the vast majority of the experience is able to be carried over from one system or one architecture to another. And contrary to popular belief, a lot of SQL-based systems can, in fact, scale, and particularly so if you're dealing with a closed or a closed cloud where you're not having to deal with the 50 billion devices that the Gartner or IDC or the analyst of the day claims they're going to be on the Internet of Things by the year 2020. Now, on the other side of the equation, we've got all these things that constitute the Internet of Things that we used to just call embedded systems. These are not big data. These are typically small devices that are running on a relatively slow CPU with a limited amount of memory. Think of your television set-top box or your network router or car infotainment systems or an industrial automation system sitting on a forklift. It's probably going to be running an ARM processor, maybe a PowerPC processor, perhaps MIPS, running at a few hundred megahertz, certainly not 3 gigahertz. Probably still going to be multi-core because more and more embedded systems are moving towards multi-core architecture. But in any case, it's not big data. And the vast majority of the time, these are purpose-specific devices. They do one thing or they do a few things, and the type of data that they ingest and the type of data that they produce is well understood. So NoSQL doesn't really bring anything to that picture for us. As I said when I was talking in the context of big data, the big selling point, or a big selling point for NoSQL is its adaptability, its ability to be able to ingest any type of data without having to know about the type of that data beforehand. But that isn't really a characteristic of the things within the Internet of Things. Think about, a set-top box. We know exactly what type of data that set-top box has to deal with. It's online TV guide type of data or the routing table in a router. So in that case, we can benefit from a database management system that allows us to define a schema, because the more a database management system knows about the type of data that it's managing, the more intelligently you can manage that data, and the more intelligently you can handle the types of queries that we want to do on the devices themselves. For example, be able to show television programs either by channel or by time or by a specific keyword or by genre and so on and so forth. So if we know what the type of data is, the database management system can do more work for us to give us the data in the way that we want to see that data. And oftentimes, these embedded systems are going to have real-time performance requirements, especially within the industrial Internet of Things, or the IIoT, as it's being referred to. So quite often, these systems are controlling manufacturing systems in real time. So they have to be able to react to events in real time. And so the entire architecture needs to be able to handle that type of requirement. And embedded database systems do that. It's also the case that most, if not all, of the NoSQL solutions out there simply aren't able to run within the characteristics that we find in these embedded systems. Again, the slower CPU with a relatively small amount of memory. Some of these NoSQL solutions have code sizes that are in the tens or hundreds of megabytes. And if you're running on a embedded system that only has, say, 64 megabytes of total memory, you're just not going to be able to run a big database management system like that on the embedded device. So I've thrown this term out a couple of times, embedded database. So when we say embedded database, we really mean a database management system that's delivered to the developer as a set of libraries. And then those libraries are linked into the application so that the database functionality exists within the application itself, in the same address space as the application itself. That's in contrast to a client-server type architecture, where the server in a client-server architecture exists in its own process, its own address space, and the client interacts with that database server through inter-process communications or perhaps a remote procedure call mechanism. And because they don't have all that client-server infrastructure, embedded databases tend to have much smaller code sizes than client-server databases. So, for example, ExtremeDB has a code size of approximately 150K for the core database runtime. If you throw everything in there, so the core database runtime with an SQL API and maybe some high availability or cluster logic, then your code size might get to be as large as 300 or 400K. But certainly, we're talking hundreds of Ks, not tens or hundreds of megabytes. small code size almost always also translates into a frugal use of memory and CPU cycles, particularly if it's an in-memory database with respect to the use of memory, because then memory is the storage mechanism for the data that the database management system is managing. So if memory is your storage medium, then you want to be able to use that memory as efficiently as possible. So in-memory databases tend to use storage much more frugally than on-disk database systems do. And when I say on-disk, I really mean any persistent storage mechanism, whether it's a solid-state disk or a spinning disk. And that small code size also translates to fewer CPU cycles being used. And that becomes really important on these embedded systems when you're running on a CPU that might only be running at a few hundred megahertz compared to 3 gigahertz for a big server-based system. And again, referring to the industrial Internet of Things, we quite often have high availability requirements. That system needs to be available. A term that's quite often used is 5 nines, which means available 99.999% of the time. And so if you have that requirement, then of course you're going to need a database management system that can support that requirement. And then within the context of the Internet of Things, you would really like to have a replication mechanism, and even better yet, an open replication mechanism, because at the end of the day, you need to get that data that's on the thing up to the server or up to the cloud to go into the big data lake for subsequent analytics. So we're going to do a little survey of some databases that are suitable for edge node database systems. So the ones I've got on the screen here are RDM from Rama, C3ACE from Faircom, Empress from Empress, and BerkeleyDB from Oracle, and the SQLite database, which is in the public domain, and our own ExtremeDB. And then I've got a number of attributes going across the rows here. So the first one is the database model that is supported. So RDM is the only one of the bunch that supports the old network model architecture. So that's also called the codicil architecture. It is a way of creating relationships between records in the database through what are called network pointers, or also known as database addresses. So you're physically linking the different records, and you follow these pointers or these links from one related record to another related record to the next related record. And following those pointers can be faster than navigating indexes. The downside of that is you end up with a very rigid database structure, and also one that's relatively fragile. So if those database pointers get compromised or corrupted, then your database is corrupted, and you can't navigate those relationships anymore. So you're trading off a performance advantage for some fragility. C3ACE is a key value pair, similar to BerkeleyDB. Difference is that with C3ACE, they also have higher level products that they build on top of the key value pairs. You can get a relational database with an SQL API, but the core product is a key value architecture. Empress is a relational type database, as is SQLite, and ExtremeDB can be used as a relational database, but we don't limit you to that architecture. You can also use ExtremeDB in a more object-oriented type of manner. You could even use it as more of a graph-type database. And in fact, RDM can also be used as a graph-type database. Graph databases are, in fact, a superset of network databases. All right, the next attribute down here is whether or not the database supports SQL, and they all do with the exception of BerkeleyDB. If you want to use SQL with BerkeleyDB, you have to pair it with SQLite. The next attribute is whether or not the database can be in memory. And the short answer for all of these is yes, but with some qualifications. So in the case of C3ACE, you can have an in-memory database, but you can never persist it, whereas the other products give you some mechanism to persist that database, whether it's on a transaction-by-transaction basis or simply being able to just save the in-memory database image off to some persistent medium. Another limitation is that with Empress and SQLite, if you create an in-memory database, that in-memory database can only be accessed by a single process. Multiple threads within that process, but only a single process. And the real limitation there is that a lot of these embedded systems are being implemented today with multiprocessing operating systems like Linux, where you can have multiple processes. But if you do that, then, as I mentioned, with Empress and SQLite, you can't have an in-memory database that's being shared amongst those different processes. Now, that's not really a concern if you're running a real-time version of an operating system like a Green Hills Integrity or a VxWorks DKM mode, which has a monolithic address space. There's no notion of processes. Everything just runs as separate tasks within this larger monolithic address space. And then the next attribute is whether or not the database supports persistent storage, and they all do. But here's an interesting characteristic. So the question comes up, can you have a single database definition that has both in-memory and persistent tables? And in some cases, yes, in some cases, no. With ExtremeDB, you can. With SQLite, for example, you cannot. If you define or if you create a database in memory, it's all in memory. And if you want to have some persistent stuff, you have to put that into a separate database definition. And then you have to be careful about how you structure your transactions, because if you have a transaction that spans both in-memory and on-disk tables, then you can break the ACID properties, which is the last line on our graph here. ExtremeDB, on the other hand, allows you within a single database definition to say, this table or this group of tables are going to be in memory, and this other table or these other tables are going to be persistent, and to be able to have transactions that span both in-memory and on-disk tables and still enforce the ACID properties. Concurrency is also an important consideration. As I mentioned earlier, a lot of these things on the Internet of Things are being created with multi-core architectures, with multiprocessing operating systems that can have multiple processes, and within each process, multiple threads. And so one of the properties under the ACID properties is isolation. In other words, changes that one task is making within the database should be isolated. They shouldn't be visible to any other task that's using the same database until the first task commits that transaction. So I should probably stop here and tell you what the ACID properties are. ACID is an acronym for atomicity, consistency, isolation, and durability. So ACID, or atomicity rather, is that all or nothing property. So we begin a transaction, we do some work, and then we commit the transaction, and all of that work that we did within that begin and that commit is treated as a single unit that either succeeds together or fails together. Consistency and isolation are intertwined. It means that every task should have a consistent view of the database, and that any change that one task is making are isolated from every other task until those changes are committed to the database. So if I'm in the middle of making some changes, you can't see any of the changes that I've made until I commit the entire transaction to the database. And then D is durability, which simply means that once a transaction is committed to the database, then it's durable. It stays in the database. You always have to take the D property, the durability, in the context of what type of database it is, in-memory or persistent. So what I mean there is that if you have an in-memory database and you pull the power plug, whatever was in memory is going to go away. So it's durable as long as the database itself, the transaction is durable as long as the database itself is durable. But that's also true with any type of persistent storage. If you have a spinning disk and you have a head crash and your disk gets clobbered, then again, your transactions are only durable as long as the database itself is durable. All right, so back to concurrency. There's different ways of implementing concurrency. There's pessimistic model and an optimistic model. So the pessimistic model says that I'm going to begin a transaction, and whatever I want to work with in the database, I'm going to proactively lock that resource, whether the resource is the entire database or a table within the database or a particular file within the database or individual records within the database. I'm going to proactively lock that so that I own it, and as long as I have it locked, as long as I own it, no other task can access that resource. If any other task tries to access that resource, then in a best-case scenario, it's going to be put into the operating system's waiting queue, and we'll just wait for that resource to become available, and then the operating system will schedule that task to go ahead and access that resource. But until it becomes available, it sits in the operating system's waiting queue. So you can have one or more other tasks that are blocked waiting for access to some shared resource. And again, there's different levels of granularity. That resource that's locked can be the entire database, and that's the case with SQLite. Or it can be an individual file, which would be the case with RDM. So if you put every table in a different file, then that's effectively the same as locking granularity at the table level, although RDM allows you to put multiple tables in the same file. So your granularity in that case can be more coarse than table level. Another aspect of the pessimistic model is the more granular your locking, the more inter-process communication there is, because pessimistic model is usually manifested by creating a separate process called a lock arbiter or a lock manager, and then there's message passing between a resource that wants to get access to some resource by sending a message to the lock manager saying, I want to lock on this, and then getting a reply from the lock manager. The exception to that is like the SQLite approach, where the entire database is being locked. In that case, you don't need any external lock arbiter or lock manager. ExtremeDB takes a different approach. We use an optimistic concurrency model, which is called MVCC, which is an acronym for multi-version concurrency control. So whereas with pessimistic, you're proactively locking whatever it is you want to access in the database, with the optimistic approach, you're not locking anything. Instead of locking, a task that wants to modify something in the database is going to get its own private copy of that thing that it wants to modify. So its modifications take place on its private copy, and then at the end of the transaction, that private copy is put back into the database, into the central pool. And that's how we accomplish isolation with an optimistic model without any locking. We make our modifications to a private copy, so they're isolated to our private copy. And then at the end of the transaction, we put the modified object back in the central pool so that every other task can then see our changes. But that introduces the possibility for conflicts, because you can have two tasks that want to modify the same object at the same time. So they both get their own private copies, make modifications to their private copies, and they both try to commit. So the first one that tries to commit will succeed, and the second one will get a conflict error. And that second task will have to retry the transaction in order to get a successful commit without any conflict. But the theory behind the optimistic model versus the pessimistic model is that occasionally having to retry a transaction because of a conflict error is going to introduce a whole lot less overhead than always having to communicate with an external lock manager or lock arbiter in order to arbitrate this concurrent access and grant and deny these lock requests. The advantage of the optimistic approach is, again, there's no locks. So no task is ever blocked by another task, which becomes really important on a multi-core system with multiple processes and multiple threads, because ideally you'd want those multiple threads to all be running and using all of the cores that are available to you. But as I said, with that locking architecture, if some resource has some task has some resource locked, every other task that wants to use that same resource is going to be blocked, and you won't be able to utilize all of the cores that are available to you. So everything else being equal, an optimistic concurrency model is superior to a pessimistic concurrency model. All right, the next one here, as I mentioned on the previous slide, within the context of the Internet of Things, ultimately we want the data on the things to make its way up to the cloud for subsequent data analytics. So we'd like to have some replication mechanism to help us out with that. And ideally, we'd like that replication mechanism to be open. And so when we talk about replication, we can talk about closed replication systems and open replication systems. So what I mean by closed replication systems is, for example, RDM can replicate between two RDM databases. Likewise for C3A, Sempris, BerkeleyDB, et cetera. SQLite doesn't have any replication at all, so you'll just have to do that yourself. ExtremeDB can also replicate between two ExtremeDB instances, but we also have an open replication mechanism so that you can replicate between ExtremeDB and Oracle, or ExtremeDB and Azure Cloud, or any other system that ExtremeDB doesn't already know about. And then we can do that replication in a number of different ways, and we're going to cover that here in just a minute, so I'll defer that conversation for a moment. And I kind of jumped ahead already, and we talked about the ACID properties, and all of these database systems implement the ACID properties, although we implement them in different ways, either through pessimistic or optimistic strategies. And then NoSQL systems, which I didn't really put any NoSQL systems on here, although you could consider C3A and BerkeleyDB to be NoSQL systems, and they both support key value stores where you don't have to predefine the structure of the database. But most NoSQL systems that are being used for big data support a different strategy that's called base, or what's called eventual consistency. So whereas all of these databases support the ACID properties, which means that the database is always consistent all the time. So even if you have two instances of the database, so you have a master instance that's replicating to a slave instance, those two instances are consistent all the time. NoSQL databases don't enforce that. They support a different notion called eventual consistency. So that's just a little note for you to make, and you can do your own independent research on what is base and eventual consistency versus what is ACID. It's kind of a little bit off topic for us today. All right, so back on the topic of replication. Again, we want that edge data to eventually become big data. So we'd like to have some means of getting that data off of the embedded devices and either into a gateway or directly into a big server. And again, whether or not there's a gateway involved is really going to be a function of how big your particular Internet of Things is. If you're in a private cloud situation and you've got a finite number of things that you need to pull data from or push data out of up to your private cloud, then you may not need that gateway. On the other hand, if your Internet of Things product is truly the entire Internet of Things, in other words, these 50 billion devices that Gartner and IDC are predicting that we'll have within the Internet of Things by the year 2020, then you're going to want a multiple-tier architecture. And what I showed here on the slide is just 3 tiers: the devices, the gateway, and the servers. But in fact, you might need an N-tier solution where the value of N depends on how big of a thing, an Internet of Things, you're trying to tackle. So within ExtremeDB, we've got a number of ways to replicate data between systems. We've got ExtremeDB high availability, and really all of the products that we talked about, except for SQLite, have some high availability mechanism. So high availability is characterized by having a single master database and one or more replicas. So all the changes are happening on that master database, and the master, in our case, is going to be one of these Internet of Things devices on the left-hand side, and the slave is going to be either the gateway or server. So the data is being produced by the edge device and being shoved up to the gateway or to the server. Another way that we can do that is ExtremeDB cluster. And what makes ExtremeDB cluster different is that it's a master-master architecture. So no single instance of the database is the master of the database. So if you have a number of edge devices that need to cooperate on a single database, then ExtremeDB cluster could be a good solution for you. So in that case, you're going to have multiple instances of the database on multiple devices, and any change made by any one of those devices is going to be replicated to every other device within that cluster. And one of these gateways or one of these servers can be just another device within the cluster. So ExtremeDB cluster doesn't require a homogeneous network. In other words, if I've got a bunch of edge node devices that are running ARM processors, they can still replicate to a big Intel-based server. So it can be a cluster of heterogeneous devices. But probably the best solution with ExtremeDB is going to be one of either data relay or what we call a persistent queue of events. Actually, I forgot one thing about clusters, so let me go back to that one for a moment. With ExtremeDB cluster, you can also define different categories of data. And what I mean by category is the replication characteristics. So within cluster, you can define what we call local tables, and local tables never get replicated. They are truly just local to the device on which they're created. And you would typically see that, for example, with configuration data. So there's some configuration data that defines how that device is going to work. And it never needs to get replicated because you're not going to do any analytics on that configuration data. The other category of data that you can define is what we call distributable data, but it's not automatically distributed. Instead, we provide a scatter-gather API. So the scatter API can be used on the edge node device, and it will, in effect, scatter its distributable data to the other edge node devices or to a gateway or a server, but only on demand. Conversely, the server or the gateway device can call a gather API, and it can gather the distributable data from the edge node devices that it's connected to. And then the third is all other data. So if it wasn't defined as being local or distributable, then it's automatically replicated. So as soon as you commit a transaction that affected some data, it's automatically going to get replicated to the other edge node devices as well as the gateway or the server. So cluster gives you a lot of control over that replication. It can either be not replicated at all for local data, it can be only replicated on demand through that scatter-gather API, or it can be automatically replicated. So it might be advantageous for you to minimize communications to use distributable data and just have a task that wakes up, say, once a minute or once every 15 minutes or once an hour and either pushes or pulls the data. All right, so now let's go back to data relay and the persistent queue of events. So data relay and persistent queue of events use the same mechanism. We essentially open up a transaction buffer for you, and we allow you to instantiate a database cursor over that transaction buffer. And within that buffer, we put markers to indicate where a transaction began and where it ended. And then you can use that database cursor to iterate over the objects and find out what happened within that transaction. If a record was inserted, you can find out that it was inserted. You can pull all of the fields for that record that was inserted. If it was deleted, you can find out what the unique identifier of that record was that was deleted, or the primary key, if you will. And if it was updated, you can also use that cursor to find out what the before and after values were of the fields that were affected by that update. And then you can use that to affect those same changes to some external system that ExtremeDB doesn't know about. And that's what I mean when I talk about open replication. So you can use that transaction buffer and that ability to instantiate a database cursor over the things that were affected by transactions within that buffer to make those same changes in some external system that ExtremeDB doesn't know anything about. ExtremeDB won't do that for you. We just give you the mechanisms to get access to that data, because ExtremeDB doesn't know anything about Microsoft Azure Cloud or MongoDB or Redis or any other external system. It's up to you to affect the changes in those external systems. We but we give you access to the data. And so the key difference between data relay and the persistent queue of events is that transaction buffer for data relay contains every change that happens in the database. Whereas persistent queue of events allows you within your database schema to describe the events that you're interested in. So in ExtremeDB, you'll define a table or a class of objects, and within that definition, you'll define events that control what information goes into that transaction buffer. And then these buffers can also be backed by persistent media. So if you've got a flood of changes that happen on your embedded device, and your task isn't able to keep up, isn't able to pull data out of that buffer as fast as the other tasks that are modifying the database are pushing data into that buffer can be backed by a file, so it overflows to a file, so you'll never lose any events. And that applies to both data relay and the persistent queue events. The other nice thing about it is you can have multiple pipes. Right? So we also call these buffers pipes. So you can have 5 threads within your task, and each of those threads can instantiate a pipe. And so ExtremeDB will be filling one end of the pipe with event information, and your task will be pulling data off the other end of the pipe and pushing it up to the gateway or up to the cloud or whatever the case may be. So there's tons of flexibility with ExtremeDB and its replication mechanisms, be it high availability, cluster, or taking control of it yourself with data relay or persistent queue events. So summarizing, because we're running out of time here, edge nodes are not big data. You don't need a big data solution for the edge nodes. What you really need is an embedded database that allows you to define the structure of the data, because you're going to know what the structure of the data is, because these embedded systems are purpose-specific. They're doing one or a few things, and the type of data that they're ingesting and the type of data that they're producing is well understood in advance. So you could use a NoSQL technology, but they really add no value in this. One of the major advantages of using a NoSQL system, or at least purported to be a major advantage, is their ability to scale. And you don't need scalability on the edge node device themselves. On the other hand, being able to define the data can be advantageous because, as I said before, the more a database management system knows about the data that it's managing, the more work it can do for you. On the other hand, upstream, there may be an advantage to a NoSQL system through its ability to deal with any new type of data coming at it. And I underlined may be advantageous on the slide here because, in fact, for a closed private cloud type situation, that may not be an advantage at all. You may not need that type of flexibility that a NoSQL system can bring. ExtremeDB not only runs on edge nodes, but it also runs on servers, and it scales very well on servers. We've demonstrated ExtremeDB scaling up to many tens of terabytes, which, of course, you're never going to see on edge nodes, but certainly on servers. And it scales horizontally as well. You can shard the database across multiple servers. So, for example, if you've got 10 terabytes of data that you need to manage, you can manage that on 20 servers with a half a terabyte on each server, keep it all in memory, and get tremendous performance, and yet still treat those 20 servers with 500 megabytes on each server, adding up to 20 or 10 terabytes of data as a single contiguous database. So whether or not you need NoSQL on the server is really going to be a function of how much flexibility you need. If you don't need that sort of flexibility, you're probably better off going with a more conventional database management system like an ExtremeDB or an Oracle or SQL Server, where you can draw from the amazingly large pool of talent that already know SQL-based systems. Conversely, if you're going to use something like a MongoDB or a CouchDB or a MarkLogic, you're going to sacrifice that ability to draw from a large pool of talent because your skills aren't really transferable. If you know MongoDB, you know MongoDB, but you're not of much use to someone that's using, or a shop that's using a MarkLogic system. All right, last item here is these edge nodes requirements are diverse, but the common theme is it's the Internet of Things. Eventually, you got to get that data upstream. So you'd really like to have a database management system running on the edge node that gives you a couple of things. One, the ability to pre-aggregate that data on the edge node. I'll talk about that more in a second. And the ability to get it up to the cloud in a reasonably efficient way. And that's where open replication becomes important. So I mentioned they're pre-aggregating the data. So let's imagine for a moment that we've got an edge node device that's measuring some sensor data. It doesn't matter what the sensor data is, but it could be pulling data off that sensor at the rate of every few milliseconds, and then having to react in real time to that data. Maybe activate a solenoid or do something in response to that data crossing some threshold. But that granular data isn't really needed in the cloud. Up there in the cloud, you may only want to know within a 5-minute window what was the minimum measurement, what was the maximum measurement, and what was the average measurement. So down there on the device, you'd like to be able to pre-aggregate that data. In other words, collapse those milliseconds worth of data into 5-second windows or 1-minute windows or 5-minute windows or whatever it might be, so that that work doesn't have to be done on the cloud-based system. The cloud-based system is going to have enough work to do as it is, aggregating data from 1,000 nodes or 100,000 nodes. It doesn't also need to collapse that data from every few milliseconds for 100,000 nodes to 5-minute windows. That work should be done on the edge. And that's where a database management system like ExtremeDB that supports SQL, even on the edge node, can help you do that work as well. If all you got down there is a key value store, like a C-Tree-Ace or Berkeley DB, then you've got to write a lot of low-level code to do that sort of aggregation on the node device itself.